So I will be recording this class, and will only share if you all say yes. Okay. Um, now, if anyone has missed, it'll be beneficial for them. All right. Now we have so far covered what exactly is electricity. Okay. Electricity is basically the flow of charge, correct, through a conductor across a particular period of time. Now the unit of current is amperes. Okay, fine. So we had seen that, okay, we had seen that current is I is equal to Q divided by T. All right, where Q is the charge flowing through the conductor and T is the time taken. All right, fine. So current, uh, the unit is amperes. Okay, and the unit of charge is coulombs, and the unit of time is seconds. Okay, so you will say that 1 ampere of current is flowing through a conductor when 1 coulomb of charge flows through that. We'll say that the current is 1 ampere when 1 coulomb of charge flows through the conductor in 1 second. All right, that is the thing. Then the next thing we saw was the different components of a circuit. All right, okay, the different components of a electric circuit. Second, okay, where we saw that if it's a battery, then the symbol would be correct. The bigger arm, see, this bigger arm stands for positive and this smaller arm stands for negative. Okay, so in a simple circuit would be something like this. Okay, we have to have an electric source, a source of current. Okay, that's a battery. So the bigger arm is the anode and the smaller arm is the cathode. Okay, so the current always flows from positive to negative. However, the flow of electrons is opposite. Okay, fine. So consider, let's say this, the current starts flowing from here all the way. It gets connected to a switch. Okay, and then to a resistor. Okay, etc. So that's a simple circuit. Now, in a simple circuit, if there's nothing inside, that means the circuit is open. Okay, when the circuit is open, there will not be any flow of current, hence there's no flow of current, correct. But when the circuit is closed, we denote by the symbol this. Okay, then immediately the current starts flowing through the resistor back into the through the battery. Okay, so the current is actually flowing through the circuit if the circuit is closed. Okay, so these are the basic few signs. And then if you want to measure the current, consider, let's say this. All right, now if you want to consider, let's say this is the resistor, right? Okay, if I want to measure the voltage, okay, the voltage or the potential difference, I will use something called as a voltmeter. Sorry, I'll use something called as a voltmeter. Okay, it's a circle with V. So all right, I will use something called as a voltmeter, and it will give me the potential difference, that is the work done, which is the work done to transport or move the current from across this resistance. Okay, so that's what we're going to see next in revision. All right, and if I want to measure the current flowing, okay, that means I'll use something called as an ammeter. All right, so these are the other devices which I used. Instrument which is used to measure current is called as an ammeter. A device which is used to measure the potential difference or the voltage is called as a voltmeter. Okay, now next thing which we saw, which we see is what exactly is potential difference. Okay, all right, so potential difference is that the Okay, so basically the formula for potential difference is V is equal to W by Q. What is this V? What is this Q? V or work done. Oh, sorry, V is voltage, okay, or the potential difference. Fine. Potential difference. So potential difference, okay, across a conductor is the work done to move charge from one end to the other end. Now, a conductor can be anything, can be a wire, can be a wire, can be a bulb, can be a tube light, okay? So, all right, so that's a conductor. Now, the work done to move a charge from one side, from one end to the other end is the potential difference. So we will say that the potential difference is 1 volt when 1 joule of work is done to move 1 coulomb of charge from one end to the other end. Okay, fine. That is from one end to the other end. Got it? So we'll say that 1 volt of one, the potential difference is 1 volt when 1 joule of work is done to move 1 coulomb of charge from one end all the way till the other end. Okay, fine. Then the next thing we saw is fine. Now the next thing we saw is what is Ohm's law. Okay, now Ohm's law is denoted by that the potential difference from one the potential difference, okay, um, between two ends in a conductor, all right, is proportional, directly proportional to the current flowing through it. Fine. So V is directly proportional to I. Got it? Okay. V is directly proportional to I, directly. So the potential difference will increase if the current increases. Likewise, the current increases, the potential difference will increase. Fine. More the current flowing, more the work is done. Got it? Now, so whenever there's a proportionality sign, if you want to change it to equal sign, we have to have something called as a constant. Okay, we have to insert a constant. Fine. So that means V is equal to a constant into I. Now what is this constant? This constant is nothing but R. R is the resistance. Okay, the resistance of the conductor. The resistance which is the resistance shown or the resistance given by the conductor to the flow of current is R. Okay, so therefore V is equal to IR. Is it clear till here? Ohm's law states that the potential difference between two ends in a conductor is directly proportional to the current flowing through it. If I was to increase the potential difference, the current increases. Okay, that means if I, that's the thing. Now, if I was to replace this proportionality sign with an equal sign, I have to insert a constant. Now, in this case, something which does not change, okay, which will only change from material to material and does not change all the time. So, this constant is nothing but the resistance of the material, okay, the conductor. So, voltage V is equal to I into R. Fine. So let's say if I'm using a tube light, the resistance of that particular tube light will be the same. It will not change. If I use a bulb, the bulb will have a different resistance, but for that particular conductor, this particular bulb, the resistance will be the same. It's not something which keeps on changing. Okay, fine. It remains constant for that particular conductor at that particular point of time. All right. In other way is we can say that we can also draw a graph. Okay, this is voltage and this is current. As the current increases, the potential difference also will linearly increase. Okay, fine. All right. Fine. Now the next thing we have is resistance. Okay, what are the factors which determines resistance of a particular material? Okay, now this resistance is something I discussed last class, that resistance is beneficial. Okay, it is because of this resistance that we are able to heat things, we are able to get light. Okay, so it is the beauty of this resistance. Yeah, someone is raising their hand. You don't need to raise your hand directly, you can just unmute and speak. Okay, yeah, anyone has any questions till now? Anyone has any questions till now?
No, sir.
Okay, great. Okay, now so we are talking about what are the factors which determines a resistance of a particular material. Okay, mostly the conductor. What is a conductor? Anything which allows the passage of electricity through it, okay, is called as a conductor. Anything which does not allow or partially allows is called as a poor conductor, or it's called as a insulator. Okay, now resistance is directly proportional to length of the material. If you take a wire, longer the wire, longer is the longer the wire, greater is the resistance. Okay, fine. And resistance is inversely proportional to the area of cross section. The area, okay, the area of cross section. That means if I was to cut the wire into two pieces, okay, if I see the thickness of the wire, if the thickness is bigger, okay, let's say this is the wire, okay, I'm talking about this. If this particular thickness is bigger, that means the resistance will be lower. Okay, bigger the area, greater the thickness of the conductor, lower is the resistance. So in short, resistance of a material is directly proportional to length by A. Now we need to get rid of this proportionality sign and replace it with an equal sign. So in that case, we will say that resistance is equal to a particular constant. Now that constant is called as rho into length divided by area. Fine. So we discussed the last thing which we stopped last class was that is what are the factors which resistance of a particular material is dependent on. Fine. And what is resistivity? Fine. Resistivity is nothing but this particular symbol called rho. Okay. So that means it is a constant, and it will vary from material to material. If so, then we stopped at this particular table. All right. So if it's a conductor, all right, the resistivity is obviously less. That means it'll offer less resistance to the flow of current. The current can flow easily. Okay. If it is an alloy, that is mixture of metals, the resistivity increases. Fine. And finally, insulators, the resistivity is so high that it always does not allow the current to pass through. Does current pass through glass? No. Can current pass through rubber? No. Can current pass through paper? No. Okay, fine. So that's the thing. Correct. Now let's come to the next thing, that is, let's discuss more about resistance. how are these resistance connected? How are these resistance? Okay, so anything which offers resistance is called as a resistor. Okay, fine. Okay, now anything which offers resistance to the flow of current is called as a resistor. Now we have in a circuit, okay, the resistors can be arranged in two particular fashions. One is called series, the other one is called parallel. Resistors in series, resistors in, or resistance in series, resistance in parallel. Now um, if I have multiple resistors, okay, I can either connect them in series or in parallel to achieve a particular flow of current. When I say series, that means I'm talking about, okay, let's say in a circuit, resistor 1, after that I'm going to attach resistor 2, after that I'm going to attach resistor 3, and so on. Okay, got it? Is this clear?
Yes,
Till now
sir.
clear? All right, fine. Now when I talk about resistance in parallel, that means I am going to do it like this. Okay, this is one resistance, and so on. Okay, so the current, when the current flows, it will flow in divided modes into each of the resistance, and then finally unite again and come again. Got it? However, if it is resistance in series, the current will not divide. The same current flows through R1, the same current flows through R2, and the same current flows through R3. Got it? Okay, clear so far?
Well, I want something to eat.
Fine. Clear so far? Can I get a yes if it's clear?
Yes, sir. And
All right. Any doubts? Any doubts so far?
parallel.
Yes. Please tell me the question. Parallel?
Excuse me, sir.
Yes. Please tell me.
Sir, that parallel. That one more time explain, sir.
Yes,
First, I
yes, sure.
said.
I'll explain to you. I'll explain to you. Okay. All right. So when you talk about parallel, that means, okay, we will say that, let's say this is first resistance, correct? First resistor. I will connect the second resistor on top of it, and I'll connect the third resistor below it. Um, that means it is, I am, from that wire, I'm just trying to divide the current. Okay, so that means when the current comes, all right, it will get divided into three. One will flow over here, one will flow over here, one will flow over here. Okay, separately into each resistors. This is called connecting resistors in parallel. Fine. Each one has its own benefit. Got it? Each one has its own benefit, which we will see it after some time. So let's just understand first that how do resistors when connected in series look like? Okay, it's very simple. You just connect one after the other. Okay, so if you want, in this case, the current will not divide. The same current will flow through each of the resistors. Fine. Now, But when it is connected in parallel, that means the current will divide. The current will divide, and it will. So the current will divide, and then it will flow into each resistor in a divided mode separately. Now, benefit over here is of resistance in series. The same current would flow through each of the resistors, correct? But perhaps the drawback is that there will be a delay. Okay, because first current has to flow through resistor 1, then resistor 2, and then resistor 3. However, when the resistors are connected in parallel, it means the moment I switch on the switch, immediately all the resistors get current flow, though maybe in divided format, but yes, all of them get the current flow. Okay, now we will understand better as to how the what exactly are the parameters which will differ when resistors are connected in series and when resistors are connected in parallel. Okay, so let's take first. Always remember this, we are going to use only Ohm's law. Ohm's law is V is equal to IR. Okay, fine, got it? Now,
Yes, sir.
all right, I'll draw this again on top. Okay, so we're talking about V is equal to IR. Remember, this is the golden rule. And we're talking about resistors connected in series. Okay, R1, R2, R3. Correct? Are we clear so far?
Where's R4?
Yes, sir.
Okay. Now, we know one thing, that the current flowing through each of the resistors will be the same. There's no division of current. Okay. Current can only, after current flows into R1, then only the same current can flow into R2, and the same current can flow into R3. We cannot have current flowing into R1 and R2 at the same time. Keep that in mind. Okay. Now, that means current is the same. Okay. The only thing which will vary is the potential difference. That means the work done to move the current. Now, keep one thing in mind. These resistors R1, R2, and R3, they are all of different. The values are different. Okay. Consider, let's say you have a tube light over here. You have a bulb over here, and you have a normal wire over here. Okay. Fine. So all of these resistance are different. Okay, some might be greater. Okay, R2 might be greater than R1, R3 might be very small. Okay, fine. So all of these are different values. Okay, now that means the work done to move current through across R1 will be different. Correct? The work done to move current across R2 will be different, and the work done to move current across R3 will be also different. Understood? The current remains the same. Is the current getting changed? No, the same current is flowing through all the resistors. Same current is flowing to R1, same current is flowing to R2, same current is flowing to R3. R1 is not equal to R2, R2 is not equal to R3. It can be the same, it cannot be the same. I'm not saying, but generally, we are saying that we are connecting different resistors of different values in series, okay, one after the other. That means when the current is flowing through R1, the work done to move current through R1 will be different. That is, the voltage will be different. The work done to move current through R2 will be different. That is, V2 will be different. The voltage or the work done to move current through R3 will be different. Okay. Therefore, if I was to measure the work done to move current across this whole thing, okay, from here all the way till here, that means Vs is equal to V1 plus V2 plus V3. Am I right?
Yes, sir.
Correct. Okay, fine. Now, That means V, okay, now V is equal to IR, correct? Fine. So suppose if you measure the voltage across, all right, now that means what is the individual resistance, or what is the total resistance, which is, just a second, all right. So what is this total V? What is V? V is equal to IR. Okay, so in this case it will be I is not getting divided, and R is equal to S. Okay, the resistance will be RS, that is the total resistance. So if I want to find out the total resistance of the circuit, okay, I need to do that. Now is equal to I R1 plus I R2 plus I R3. All right, fine. Now I Rs is equal to I R1 plus R2 plus R3. Is that fine? I is common for in both, in all three, so I can remove I, keep it outside. Is that understood?
Yes, sir.
All right. So I is common in both sides, so I can remove I. So that means, sorry, 1 second. This board is stopping over here. Okay, I'll continue over here. All right. So that means Rs is equal to R1 plus R2 plus R3. Okay, it's simple. So basically this is a simple derivation. So when you connect resistors or resistances in series, the collective resistance or the total resistance is simply the sum of the individual resistances. Okay, got it?
Yes, sir.
Fine. Now let's see the next one, that is reconnecting resistance in parallel. Okay, now we have this simple, okay. Now over here in this case, Ohm's law is V is equal to IR. All right. Now over here, okay, over here, if you go and see what is the voltage dividing, if I was to measure voltage, it is remaining the same. Yes, individual voltages might vary. However, what is dividing over here? Current is dividing. Okay, that means I, whatever I is getting divided into I1, sorry, right? So this I is getting divided into I1, I2, and I3. Okay, so the total current which is flowing through this circuit is the summation or the or adding I1 plus I2 plus I3. All right, that makes sense. Okay, but what is this? What is I over here? If we come from Ohm's law, I is equal to V by R. Okay, fine. V by R. Now, in this case, we know that if I was to measure the voltage from this point, it is the same as measuring for R1, R2, and R3. Fine, keep that in mind. The work done to move, the current divides. Okay, so accordingly, the current is dividing, the current is changing, voltage remains constant over here. So the work done to move the current across the circuit is same for R1, R2 and R3 because they are connected in parallel. However, in series, the work done differs, fine, because the current is undivided. Over here, the current is dividing accordingly, fine. So in that case, V by Rp. So here we want to find out what is the total resistance of this circuit. That is, what is the total resistance when you're connecting R1, R2 and R3 in parallel? What is the total resistance which is offered? It is not as easy, it's not as simple as just adding up R1, R2 and R3 as we see it in series, because here they're connected in parallel. So here in this case, V by Rp is equal to V by R1 plus V by R2 plus V by R3. Okay, fine, clear? Next thing we have is V by the next thing we have is V by Rp is equal to V, take out common, 1 by R1 plus 1 by R2 plus 1 by R3. Got it? Now, can you cancel V's on either side? Yes, we can because they are common. Finally, 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Fine? Okay. So in this case, we cannot say that when resistors are connected in parallel, and if you want to calculate the total resistance of the circuit, you cannot simply add each one. You have to reciprocate. Okay, that is, keep it in the denominator, 1 by R1 plus 1 by R2 plus 1 by R3. When you see a few examples, we will come to know. Okay, let's see this case.